Hello and welcome. Today we're going to be looking at the unit test for applications of integration, one of the topics on AP Calculus AB and BC. As always, we're going to be going through all of these questions to help you understand how to do these problems, how to approach and solve these kinds of problems. You're going to learn how to apply integration in various different situations, and with that, let's get started on our first question. Let R be the region enclosed by the line x equals -2, the line y equals 1, the line y equals 3, and the curve y equals the square root of x plus 2. Okay, so we're trying to find all this area, and now we're going to rotate R about the line x equals -2. X equals -2, this line right here. Alright, let's think about that. So how do we go across doing these kinds of problems? Well, let's see. So this is a disk, right? So there's no space in between here, so it's going to be a disk. And every time you do that, you're going to get a circle. All right, so this is going to become a circle. Right, this is going to become a circle, and then a circle. Okay, now how do we figure out what the circle is? Well, we have the radius right here, the distance from the curve to the line y equals 2. I mean x equals -2. Okay, so essentially, we're just trying to find the distance between the curve and x equals -2. Well, how do we do that? Let's think about how we do that. All right, so we're going to go in terms of y. Right, in terms of y, we're going to try to solve this. So if I was to write an equation where x is the final variable and y is kind of like the independent variable, I would square both sides, and then I get y squared equals x plus 2. So then y squared minus 2 equals x. Okay, y squared equals minus 2 equals x. Right, so now what? Well, now what is that we realize that we're going from y equals 1 to y equals 3. Okay, so we're starting at y equals 1, we're going up to y equals 3. For every single one of those, you're going to have a circle. Okay, and what do we know about that? Well, for those circles, you're going to have, it's going to be pi r squared, right? So pi, we can put the pi outside, right, because we don't really need to put it in there. It's a constant. Pi r squared. Now, what is the r? The r is the distance from here to here. All right, so it's the difference in the x coordinates between the curve and the x equals -2. So if we've written the curve as y squared minus 2, and we've written the line as -2. So if we do y squared minus 2 minus -2, which would give us y squared, then that is going to be the difference, right? So if I write y squared down, that's a y squared as our radius. Okay, why is y squared our radius? Well, at x equals 1, or at y equals 1, right, you're going to have the distance between the curve and that line to be 1. At, say, y equals 2, right, then the distance between -2 and the curve is going to be 4, 2 squared. So y squared is going to be our radius. Now, area of a circle is pi r squared, so we're going to put a pi outside. We have y squared squared, and we're integrating this with respect to y. So it's going to be pi times 3 of y fourth dy. All right, now we could use our calculator here, right? So if we wanted to if we just wanted to pull out our calculator, we could do that. But we could also just figure it out ourselves. And, like the antiderivative is going to be 1/5 y to the 5th of y to 4. That's the antiderivative. But the calculator is here. We might as well just use it. All right. So we have y to the 4th dy 1 to 3. And then you're going to multiply it. So you end up with 48.4 pi as your answer. 48.4 pi. And we can keep going. Okay. Let f of x equals 3x squared minus 8x squared minus 3x plus 12, and g of x equals 4e to the x plus 1 times x minus 3 plus 2x plus 2. Let R and S be the two regions enclosed by the graphs of f and g as shown in the graph. Find the sum of the areas of regions R and S. Well, see, what we could do is we could find the intersection right here, and we could find the area between f and g for R, and then we could find S, but I don't want to, right? Because that's really tiresome, and you don't have to. What I'm going to do, right? So I'm going to go to the plot, right? So where you can type in these, you go to just y equals right here on TI-84 plus. I'm going to type in the f of x, 3x cubed minus 8x squared minus 3x plus 12. Second one is 4e to the x plus 1 times x minus 3 plus 2x plus 2. So I have 3x cubed minus 8x squared minus 3x plus 12, and then 4e to the 1 times x to the 3 plus 2x plus 2. And now what I can do is I can take the integral from negative 1 to 3 of the absolute value of the difference of these two functions. Right? Why does that help me? Well, see, it helps me because instead of having to know, instead of like when this part gets positive and then this part goes back negative, well, now they're both positive because absolute value. So it's a cumulative thing. And the answer that I get is 24. Right, 24. I don't know why they said round to 3 decimal places. I didn't get 3 decimal places. I just got 24. 24. That's our answer. And we can keep going. The average value of sine x on the interval negative 6 less than or equal to x less than or equal to negative 1. This is where we use this thing called integral over interval. All right, integral over interval. That's what it is. Right, so that's how we calculate the absolute value. Right. So let me write this down. So how we do it? The integral is from negative 6 to negative 1 of sine of x dx. Sine of x dx. And the interval is from negative 1, and then you subtract negative 6, so it's going to be 5. Right, so I think the interval part is kind of intuitive. You're dividing over the amount of stuff. Now, how does the integral part work? Well, essentially, you're finding the area under that curve. Okay, you're finding the area of all that was there. Okay, so you're finding the area of everything under that curve, all the sine x values added up. Right? Because if you take the area under the curve of sine of x from negative 6 to negative 1, that's like adding all of the different values of sine of x from negative 6 to negative 1. And now you're dividing that by 5, which is the interval. Right? And that gives you the average value. So I do this. So in the denominator, I just have 5. That's the length of the interval, that's 5. And then in the numerator, well, sine of x, the antiderivative of that is negative cosine of x. So it's going to be negative cosine of negative 1 minus negative cosine of negative 6. Or just cosine of negative 6 minus cosine of negative 1 over 5. And then since cosine is an even function, right, meaning that on both sides it's up, so it's the same. So cosine of negative 6 is the same as cosine of 6. Cosine of negative 1 is the same as cosine of 1. I'm going to be left with cosine of 6 minus cosine of 1 over 5. And that's it. So our answer is going to be B. And we can move on to the next question. All right. What is the area of the region bound by the graphs of f of x equals square root of x plus 2, x minus 2, g of x equals 14 minus x, and x equals 2? Okay. So what do we have here? What do we have here? Well, let's think about where they intersect. All right, let's think about the intersections. Well, one intersection that I can see is where's an intersection? Intersection seems to be at x equals 11. All right, so intersection x equals 11. Right, if you plug in x equals 11, then f of x and g of x intersect. So essentially, you're having an integral from 2 to 11. That is the area of the region bound by the graph. So the absolute value of f of x minus g of x, which is going to be so f of x is square root of x minus 2, and then you're subtracting that by 14 minus x, and that's going to give you, at the end, it's going to give you 49.5, or 99 over 2. 99 over 2 is our answer, and we can keep going. Which integral gives the length of the graph of y equals e to the 2x between x equals negative 2 and x equals 0? So this is going to be an arc length problem. All right, so if you are an AB, not BC, then you don't really have to worry about this problem. You can kind of skip ahead to the next problem because arc length is not a topic on the AB curriculum. It's only on the BC curriculum, right? But so we're gonna figure out how we do arc length. So how you do arc length is so first of all, I'm gonna explain the concept behind arc length. So the concept is that you take the derivative of the change, right? So in if you're doing this in like a Pythagorean theorem kind of way, the difference would be the square root of x squared plus y squared. Okay. Now you're going to take the derivative of x squared and the derivative of y squared, or derivative of x and derivative of y, and then square that. So you end up with the square root of of dx squared plus dy squared. Okay. And then you take the integral of that, right? And that adds up all of the different changes that make the arc length. Now that's how it works for like parametric functions, right? You have dx and dy. Now when you have x is defined as you don't not really defined as anything, what do? You're trying to find it between negative 2 and 0. You put up the square root. Okay, so you have the dx, right? What's the derivative of x? Well, it's just 1. So you have 1 squared, 1. And then you have the derivative of y. The derivative of y is going to be 2e to the 2x. And then you square that. So then you get 4e to the 4x. And that's going to be dx. And that's your integral, which is not that one. This is that one. And that is our answer. And we can keep going. All right. A particle moves along the x-axis with a velocity v of t equals t squared over sine squared t plus 2. The particle is at position x equals 3 at time t equals 2. What is the particle's position at time t equals 7? Well, let's see how we're going to do this. Well, this is called accumulation. Right, that's what this unit is called. We call it accumulation. And how does it work? Well, it essentially works by saying I'm going to have the position at time equals 2, which is 3, and I'm going to add the change between 2 and 7 of v of t dt. And that's going to give me the position at 7, right? It makes sense, right? You're having the initial position, and then you're adding the integral, which is really the integral of the velocity, which is really just the final position minus initial position. So you're doing initial position plus an integral that means final position minus an initial position. The initial position is going to cancel out, and then you're just left with final position. So I'm going to take the integral from 2 to 7 of t squared over sine t squared plus 2 d of x, and then I add that to 3, and I'm going to get 58.580. That's 5 8s there. 58 58.580. And that is incorrect. And let's think about why that's incorrect. All right, let's think about what we messed up on. What why 58.580 is incorrect. So if you go back to the accumulation equation, right, you have to make sure that you're doing the accumulation the right way. So accumulation is the starting position, and then you add the integral of the velocity of the change, right, and that's how you get to your final thing. Okay, so how are we going to do that? Well, what we can do is we can rewrite the equation. So x squared, I'm going to have sine x squared plus 2. Okay, now I'm going to do that. So make sure you type in the equation right. That's what I'm checking right now, just to make sure I typed it in correctly. And then if we try that again, 2 to 7, right? So from time t equals 2 to time t equals 7. And we try that out. And you still get 58.580. So let's keep thinking about what we did wrong. All right, so this is how the accumulation idea works. Okay, that's how accumulation works. And then you see you're having this plus 3, right? You're evaluating it the same way, so that they get 47.772. All right, 778. Well, I got 55.580. So that is just a malfunction with the fact that I am in degree mode right now, and for calculus, you're supposed to be in radian mode. All right, so that is my fault. Right, so if you try it again in radian mode, right, and then add the 3, then you get to write 50.778. Okay, and that is correct, 50.778. So make sure you are in the right mode. Right, I know it might sometimes be tricky, right? Like I had a physics class, and they use degrees, right? So you need to make sure you're in the right degree mode. You're in the right mode before you start doing this kind of stuff. All right, so now we have a curve 144y over y squared plus 4 squared. What is the area bounded by the curve? The y-axis, the line y equals 0, and the line y equals 6. Let's see. Well, we're essentially going from taking integral. We're going from 0 to 6 of this 144y over y squared plus 4 squared. 144y over y squared plus 4 squared from 0 to 6. And you're just going to add that up every time, right? That is it. Right? So you're just going to type that into your calculator. From 0 to 6, 144y over y squared plus 4 squared. Right? And you get 16.2. And we can move on to the next question. Number of people exposed to a certain illness is increasing at a rate of R of T people per day. T is the time of day. At T equals 12, there were 115 people exposed to the illness. What does 115 plus integral from 12 to 20 of R of T d of T represent? Well, the rate is R of T, so if you're doing 12 to 20, that's going to be like the number of people at 20 minus the number of people at 12, plus 115, which is the number of people at 12. So you're just going to be left the number of people exposed at 20. All right, that's why knowing how accumulation works, comes in handy. So that's the number of people exposed to the illness at 20 days. All right, let f of x equals x over 2 and g of x equals ln x plus 3. Let R be the region enclosed by the graphs of f and g and the lines x equals 2 and x equals 5. Region R is the base of a solid. For each x value, the cross-section of the solid taken perpendicular to the x-axis is a rectangle whose base lies on R and whose height is x over 2. Okay. Okay, so what do we do here? And how do we think about this kind of problem? Well, we know that for any x value between 2 and 5, right, the base lies in R, it's perpendicular to the x-axis, so the length is just going to be, length of the rectangle base is going to be ln x plus 3 minus x over 2. And that's the length of the base, And then, of course, you're going to multiply that length of the base. You're going to multiply the length of the base by the height, which is x over 2. X over 2. And that's for every x value between 2 and 5. D of x. Okay? So integral from 2 to 5 of ln x plus 3 minus 0.5x multiplied by 0.5x, and then d of x, and that's going to give you, or actually you don't even need to find it out what it is because that's for the integral. So you don't have a pi because you're not doing like a circle or something. You don't need pi, but you do have 2 to 5 of ln x plus 3 minus pi over 2. It's not squared, but it's times pi x over 2. So that's our answer, and we can move on. The velocity of a particle is cosine of t at t equals pi over 2. Position is 2. So I'm going to find the position function, which is going to be sine of t, and then at pi over 2, sine of t is 1. So I have to add another one to get for the constant. Position of the particle, s of t, or I wrote x of t, but it's going to be sine t plus 1. Sine t plus 1. That's it. And we can keep going. What is the area of the region between the graphs of f of x equals square root of x plus 1 and g of x equals 2x minus 4 from x equals 0 to x equals 3? This is called a calculator. You use the calculator. Okay? I don't have to write down a single thing. I'm just going to use the calculator. So I'm going to have two functions, square root of x plus 1, and then 2x minus 4. That's for y1, y2. Then I have 0 to 3 of absolute value of y1 minus y2. And I get 7.6667 which is going to be 23 over 3, or answer choice B. And we can keep going. Hey, let R be the region enclosed by the curve y equals x squared minus 5x plus 3, and the line y equals x plus 2. Right, region R is the base of a solid whose cross sections perpendicular to the x-axis are squares. Which one of the definite integrals gives the volume of the solid? Alright, so the perpendicular to the x-axis is going to be x minus 2 minus x squared minus 5 minus, okay. So x minus 2 minus x squared, so you're going to have a negative x squared. You're subtracting negative 5x, so you're going to have 6x, and then minus 2 minus 3. So it's going to be negative x squared plus 6x minus 5. Alright, and it's going to be squared because it's a square. And you're going from here to there. Alright, where does it intersect at? Let's see. Well, it intersects at 1 and 5. Alright, so from 1 to 5, and that's it. And we can keep going. Let R be the region enclosed by the y-axis, the line y equals 2, the line y equals 3, and the curve y equals the square root of x. You have this. They're telling us that a solid is generated by rotating R about the y-axis. The y-axis. What is the volume of the solid? Exact answer in terms of pi. Okay, so the distance from the y-axis to the curve, right, that's going to be that x distance, which is going to be y squared equals x. Okay, so we're really just doing y squared. So we're going to take an integral from 2 to 3 of y squared, because it's going to be a circle, right? Circle, and x dx. And that's going to be 42.2. 42.2 pi. And we can keep going. Right, the shaded region is bounded by the graph of the function f of x equals 2 plus 2 cosine of x and the coordinate axes. What is its area? Well, it's going to be the integral from 0 down to where the 2 plus 2 x touches the coordinate axes, which is going to be where cosine of x is negative 1, which is going to be at pi. So, the pi. of 2 plus 2 cosine of x dx to radian mode, and you get 6.28318 on and on, which, if you know about pi, that's just 2 pi. 2 pi, that is it. 2 pi. And we can keep going. Nara received the following problem. A particle moves in a straight line with a velocity v of t equals negative t to the fourth plus t to the cubed meters per second, where t is a time in seconds. At t equals 0, the particle's distance from the starting point was 4 meters in the positive direction. What was the particle's position at t equals 9 seconds? What expression should you use to solve the problem? Well, this seems like an accumulation kind of idea. All right, so we have from 0 to 9, integral from 0 to 9 of v of t. Right, that's correct, right? This expression also has that, and this one has the initial 4, right? So you have to add the initial plus the change, and you get that accumulation. So that one is correct. These two aren't correct since they just mess with velocity, not position. And we can keep going. Consider the following problem. The depth of the water in Harsha's birdbath is changing at a rate of r of t equals 0.5t minus 0.1 millimeters per hour, where t is a time in hours. At time t equals 0, the depth of the water is 35 millimeters. What is the depth of the water at time t equals 3 hours? What expression can we use? Well, accumulation again, 0 to 3. Right? At time t equals 0, time t equals 3, so 0 to 3 of r of t plus the 35. So that's our answer. And we can keep going. Region R is enclosed by the line y equals x and the curve y equals x squared. Okay. What is the volume of solid generated when R is rotated on the x-axis? Okay. Okay, so now we're getting some interesting stuff. Right, this is some really interesting because now we've left behind the realm of disks, and now we're going to start talking about washers. Right, I know that washers is a topic that every single calculus student hates, but bear with me because once you get the hang of it, it doesn't become better because you still don't like it, but it becomes easier and it becomes more fluid, right? All right, so how are we going to do something like this where you're writing around something that's not connected to it, right? It seems like how would you even do that, right? How you do it is this is why it's called washers, right? Because you have a washer, you have a circle in the center, and you have a circle on the outside. So you have a circle in the center and you have a circle on the inside, right? You set up an inner circle, which usually has radius lowercase r, and an outer circle, which has radius uppercase r, right? And then the area that's left there is just going to be the big R squared minus the little r squared times pi, because you're doing the area of the whole circle minus the area of the circle, the part of the circle that's also inside there. So what do I mean by that? What do we mean by that? Well, for every single one, we have the outer radius, big R. So we're rotating on the y-axis. That's going to be y equals x. So we're rotating it perpendicular to the x, so we need to express in terms of x. So it's going to be, so it says the integral of from 0 to 1, because we're on x, of this x as our radius, right? That's our small radius, and we're squaring that. Okay? And now we're subtracting that by the center, the inner radius, which is x squared, and squaring that. Multiply by pi, and then dx, and what you get is essentially like this. This is what you get. All right, so this is the inner radius right here, the outer radius, the big one. This is the inner radius. From 0 to 1, you have the pi over there, and then you're just finding this. All right, now I'm going to take my calculator, and I'll plug these numbers in. Oops. I'm going to plug this in. 0 to 1 of x squared minus x to the fourth dx, and that is going to be 2/15. 2/15. And we can move on. Let R be the region enclosed by the line y equals pi over x over 3, the line y equals 4 minus x, and the x-axis. So let's generate by rotating R around the line x equals 5. Alright, so when we're rotating around the line x equals 5, that's parallel to the y-axis, right? So we're going to have to do stuff in terms of y. So what does that mean? What does that mean? It means, so we're going to set up an integral from what? Well, the solid is going to be from 0 to 1 in terms of y. All right, 0 to 1. The the outer radius, sorry, is going to be the distance between is going to be the distance between this one right here. Will be this distance. Okay, now how do I say that? Well, the x is going to be 3y, so it's just going to be 5 minus 3y. 5 minus 3y squared. And then for the inner radius right here, it's going to be 5 minus the 4 minus x, which is just going to be 1 plus x. All right. So the radius is going to be 1 plus x, right? So it should be. So you start out here with a radius of 2, or yeah, sorry. Sorry, I'm just getting myself confused. See, if you isolate x, then you get 4 minus y, and then you have 5 minus 4 minus y, which is y plus 1. So y plus 1 is the radius. Y plus 1 is the radius. All right, so 5 minus 3y squared minus y plus 1 squared dy times the pi, which is going to equal, what is that going to equal? So 5 minus 3y squared, y plus 1 squared, going from 0 to 1 of the first one minus the second one. All right, and then you do that and you get 32 over 3. 32 over 3, and we can keep going. The base of a solid S is the region bounded by the parabola x squared equals 8y and the line y equals 4. Cross sections perpendicular to the y-axis are equilateral triangles. They're perpendicular to the y-axis, so we do this in terms of y. And so we do this in terms of y. So we have, in terms of y, we have an integral right here that's going from 0 to 4. We start at y equals 0, we end at y equals 4. And each one is going to be spanning between the two x's. All right, so this part right here is going to be, that's x, which is going to be square root of 8y. This is also the square root of 8y, so it's going to be 2 square root of 8y. 2 square root of 8y is going to be the distance between, is going to be the side length of the equilateral triangle, which then you square and multiply by root 3 over 4, because that's how you do with equilateral triangles. Equilateral triangles. Root 3 over 4, that's your triangle, and you're going from 0 to 4 with that. Okay, so if you're going to do that, you get 2, 8. Alright, so you get 2 times the square root of 8x squared dx. Alright, or square root of 2 times square root of 8y squared dy. From 0 to 4, that gives you 256 divided by 4 times the square root of 3 is going to be 64 square root of 3. 64 square root of 3, and we can keep going to the next question. The number of hours of daylight in a town changes at a rate of 1 over 20 cosine t over 60 plus 2 hours per day, where t is the number of days since January 1st. By approximately how many hours does the daylight increase between t equals 240 and t equals 300? How much does it increase? Well, we have t equals 300, so we can plug that in and we get 1 over 20 cosine of Well, actually, no. That is that is the rate. That is the rate. So if I want to do the opposite, if I want to if I want to find the amount it changes by, then I have to take the antiderivative, which is going to be 3 sine t over 60 plus 2. T over 60 plus 2. Okay, now what am I going to do with that then? Well, 3 times sine t over 60 plus 2. Then I plug in my 300, I plug in 240, and I get 3 sine 7 minus 3 sine 5. 3 sine 7 minus 3 sine, 3 sine 7 minus 3 sine 6. And our answer is going to be choice D. Alright, so that was the unit test on the applications of integrations. We dealt with washes, we dealt with shells, we dealt with area between the curves, average value, accumulation. All these kinds of topics fit into one unit. This is one of the hardest units, one of the ones that students hate the most, simply because there's so much, and every single problem you have to do so much to get the answer. But I hope you learned something from this video, and I hope you enjoyed it, and I'll see you next time we continue looking at more topics on AP Calculus, AB, and BC. I'll see you then.